about the geology of Morgan Hill?
Yeah. All right.
Do you believe them?
Do I believe them? Sorta.
I don't believe you. Are we ready to hear about geology of Morgan Hill?
First, thank you and welcome to everyone coming to our Leadership Alumni event. And I want to extend a hearty welcome to everyone from Leadership Gilroy. It's wonderful to have an event with Leadership Gilroy. Thank you, Leadership Gilroy, for coming. We can network, celebrate, and our common bond as leadership group. So thank you again. Hopefully we can do this more often. A couple things I want to say too. First, August 6th, Leadership Morgan Hill is having our capstone lead event this year where we're honoring Mike Johnson at another winery down the street. August 6th at Jason Stevens. Yeah, Jason Stevens. Roy, you okay with that, Roy? Okay. So this is going to be an event, August 6th, dinner, party, usual suspects. It'll be a fun event to fellowship and honor Mike Johnson, owner-operator of Ace Hardware and Johnson Lumber in Morgan Hill, and he really represents who we are as leadership programs in general. Also, and we have more information about that around here if you're interested. Also, I want to put in a word for our Leadership Morgan Hill class of 2011. They have their project right going into full swing here. Bricks for Our Future. So it's an excellent project. You can find out more about it and you can talk to them. Some class members are actually here tonight. They can tell you about their brick sales and what that means, what they're going to do with it, and why that fits into our community in Morgan Hill. So our program, John.
I just wanted to
Q&A. Okay, already.
I just learned something tonight about Gilroy's leadership.
Okay.
Every year, I need to share this. Every year, Gilroy, each class has a slogan, and I happen to be sitting with the class of 2007, and their motto is
007, License to Lead.
That's great or what? I love that. Every year has a slogan.
That's good. Okay, license to lead. Okay, I like the slogan. Way to go. Was there a James Bond movie released that year?
After a few more drinks, she'll share.
Yeah, she'll start issuing licenses. Right.
Yeah.
No fee. Okay. So our speaker tonight, Peter Anderson. Peter Anderson is our local expert on dirt. and rocks. And we do have special dirt and rocks here in South County. Peter is a practicing geologist for well over 35 years. He has a firm in Morgan Hill, Pacific Geotechnical Engineering. It is the largest, the best, and the only geotechnical engineering firm in Morgan Hill.
And the best still.
And the best still, indeed. Correct. Peter is a Peace Corps volunteer. He went to Nigeria in the early days of the Peace Corps. I really like that. That speaks to me volumes. Peter was named Man of the Year in Morgan Hill a few years back, so he is clearly very involved in the community here in all of South County, Morgan Hill in particular, and Gilroy even. So everyone, welcome to Peter Anderson.
Most of what he said is actually right. Yes, I'm a geologist. My life is dirt. Oh, I'm sorry. It says, dirt is my life. Sorry. I had that wrong. I'm impressed that everybody would be here tonight, what with championship hockey game going on and, a championship debate going on in New Hampshire right now. But I guess, hey, if that doesn't turn you on, watch out. This is going to be... So, yes, I am a practicing geologist. That means I do make my life, my living out of doors. Well, less so nowadays. I've graduated from the point where I do a lot of field work. The staff does that, and I have to sit in back and do the analytical part. But it is possible to earn a living in the profession of geology. I'm actually an engineering geologist, which differs a whole lot from mining geologists and petroleum geologists and environmental geologists. But you don't need to know the details about that. You're here to hear about the geology locally here, rocks and soil, yeah, dirt. And so I normally would have maps and charts, cross sections, illustrations, because geology is a three-dimensional feature. You know, east-west, north-south, top to bottom. We always say that the work we do in engineering geology starts at the ground surface and goes down. The third dimension is really important to us. So, but without having illustrations, I'm going to wave my arms a lot and follow my notes if I can. First and foremost, the geology of the locality here begins with the geography. And it's pretty simple. Most of us live in a valley, Santa Clara Valley. It's just over there. Some live in the mountains on the west. That's Santa Cruz Mountains. That's where we are right now. Some live on the other range, on the other side of the Santa Clara Valley, the Diablo Range. So we got mountains, valley, mountains. Pretty simple. And it's a fairly linear valley. You know, it goes all the way down to Hollister and then runs north to San Jose and into the San Francisco Bay. Actually, the bay is a continuation of Santa Clara Valley. The sea level goes down a couple hundred feet. Our valley will go all the way up to the Golden Gate. And you won't need a boat to get to Alcatraz, if that's your destination. So geology has something to do with our mountains, valley, and mountains. It's a linear valley. Linear. There's not much in Mother Nature and the geologic sciences that is really linear, except for faults. Earthquake faults. Yeah, we got a few of those around here. Like the Calaveras Fault runs up the east side of the Santa Clara Valley just into the foothills, and that has been a major player in the formation of our valley. Our valley is parallel to the Calaveras. The San Andreas Fault's just right over there in the Santa Cruz Mountains. So we got mountains, valley, mountain, if you will, fault, valley, and fault. Of course, I'm overgeneralizing. This is if you with the camera. I don't want to be quoted on this. So, going on from here, what characterizes the mountains versus the valley? Mountains are underlaid by bedrock, meaning you go out, if you want to dig a hole in the ground, you dig your shovel and you dig down. Pretty soon you're going to hit rock. There's a variety of bedrock types. I don't need to go into that now. Whether you're on this side of this mountain range or that mountain range, you are in bedrock terrain. The valley, flat valley, is full of dirt. Sediment, if you will. Alluvium. We call it alluvium because the sediment that forms the valley was carried to the valley by streams. There's something Greek about the origin of that word that means river carried by water. So what is alluvium? I happen to have some. A lot of stuff here. Rocks, sand, dirt. It's actually clay, silt, sand, and gravel. And I will pass these around. I got about a dozen or so boxes with earth materials, we'll say. They get better as the talk goes on. This is alluvium. And if you go out and dig in alluvium, you can dig all the way down through, with your shovel, all the way down through the alluvium in this valley and reach the bottom of the valley where you find bedrock. That's several hundred feet, so you probably won't want to try that. But you could, physically, with a pick and shovel, do that. That's the major distinction between the alluvium and the bedrock. Okay. Notes.
Hey, Peter, the company Granite Construction, you know, the road, is that what kind of material they use?
They use, no, they're located in an area where they have a quarry that actually has granite, but they will do grading, construction, earthwork construction with any kind of dirt. Sorry. Dirt is the stuff that you get on your clothes and wash off. We deal with soil. Technical difference. All right. Our valley, our linear valley, as always, as almost every valley, has a stream running through it. From the upper end to the lower end. In our case, well, the only thing that makes water flow in a creek is gravity. If you try to see a make river flow upstream. Tough job. So gravity generates the force that moves water. And so every normal valley has a creek running through it. In our case, we have 2 creeks running through the valley. Geology Creek and Coyote Creek. And there's some quandary about that. So that's chapter 3. Now we're going to shift over to chapter 2. And that is the iconic landform that we have in Morgan Hill. El Toro, you know, the volcano over here. Who's laughing? Come on, everybody calls it a volcano.
I call it Morgan Hill, and I had until I got educated when I got here.
Very good. Well, just to confirm with you, everybody, the geology of El Toro, it is underlain by, composed of 90%, 95% volcanic rock. Here's a big sample, which you're welcome to come take a look at some time. And a smaller sample, 2 of them. They're not really enchanting. They look sort of like grungy rock. And that's all it is. I have 2 samples to pass around. And by the way, I know how many boxes there are, so when it's all done, I expect them. You'll see one of these. It has a bunch of fossilized gas bubbles. Lava, volcanic rock erupts from below the earth, but it always has some amount of trapped gas. Sometimes the gas escapes, sometimes it doesn't. And this one still leaves a little gas bubble holes. They're fossil gas holes. Play with that one for a little bit. So, this is volcanic rock comprising El Toro. But I will make a prediction. El Toro will not erupt. That you can quote me on. The volcanic lava that we have here, and it's called greenstone. It's the origin of the name greenstone is something you don't need to worry about. Everybody else calls it red rock. Okay. The volcanic lava that erupted, that forms El Toro, erupted about 5,000 miles away from us, west, southwest of us, south of the equator, about 100 million years ago. How do we know all that? When you look at the rocks, you can tell. We know that it's we know that it was formed way out in the South Pacific because it is interlayered with fossils. And those fossils have been calibrated to the temperature of the ocean where those creatures died and got buried. And we know that it's either 14 degrees plus or minus is the way it was done. Either north of the equator or south of the equator. They couldn't determine, but that was, however, we also know that it was erupted onto a plate, as in a tectonic plate, as in continental drift, as in plate tectonics, as in it erupted onto the ocean floor 100 million years ago, 5,000 miles away. And in the intervening time, that continental plate, called the Pacific plate, has been moving steadily towards us, the North American plate. And it crashed something around 15 million years ago. And all you have to do is a little bit of distance equals time by time velocity. You multiply it out and you figure how far this has traveled. And so we know that it's 14 degrees south latitude doing the triangulation. So, and it erupted all that time ago under the ocean, way out there. So, number one, it is 5,000 miles away, removed from the source of the lava. And that's also 100 million years of time removed from the source. So it's pretty easy for me to make that prediction. We do have some volcanic rock around here, however, that was formed locally. Called basalt. And actually the greenstone that you see was originally erupted as a basalt. But over the 100 million years, things happen. That much time, change happens to all of us. So this basalt is only 2 or 3 million years old, and it's commonly found on the east side of the, well, let me just say, in the Diablo Range. And this has nothing to do with the volcanic activity that created El Toro. It has everything to do with a series of volcanoes that erupted around here 2 to 3 million years ago as the San Andreas Fault was being formed. San Andreas Fault has not been here forever. It started forming about 15 million years ago. Something in the range of 5 million years ago, it struck us in this area and began forming to the farther to the north. And while it was here, that ended volcanic activity. There is one reminder of that ancient volcanism: Gilroy Hot Springs. That's still, springs often form along faults because faults break rock, form conduits for water to move, down to up. And where you have a fault, you can have a spring, very common, and where that fault is near ancient volcanic activity, you wind up with hot water. See, aren't you glad you came here and didn't stay for the hockey game?
So the Gilbert Hot Springs are in the Diablo Range, which has the Calaveras Fault, but it's formed by San Andreas.
The Calaveras is a spin-off. Are you trying to confuse me?
I apologize, I thought you said that the Gilbert Hot Springs was the result of the San Andreas Fault explaining.
Yes.
But around the Calaveras Fault over here?
The Calaveras is a spin-off, if you will, a splinter fault of the San Andreas.
Okay.
And actually the Calaveras Fault is a splinter fault of the Madrone Springs Fault, which preceded, and Madrone Springs Fault is the one that is giving us the hot water.
Okay, thank you.
Are there other mountains or ancient volcanoes that came along with Mount Diablo for that same eruption in the area?
The evidence of that ancient volcanism has mostly been eroded away. I mean, it's had 2 to 3, maybe 4 million years to happen. You wouldn't last very long after 200 or 300, 2 or 3 million. So, but most of it's been eroded away. But there are more volcanic areas farther to the north. You get up into Sonoma County. The geysers. You're getting me off track here.
Sorry.
Last question, and then I got to move to this.
All right. Sorry, I'm slightly confused. So El Toro was a volcano, or El Toro is the result of a different volcano?
See, that's down here at the lower part. I'll get to that.
Are you a plant?
I mentioned that there were fossils amongst the greenstone, the lava that erupted 5,000 miles away from us. Those fossils were contained in limestone. Limestone. The white rock here. You can see the layers. Each layer represents one episode of deposition in the ocean where there was a change in the oceanic temperature or chemistry, and all the little fossil or all the little creatures that have a calcium type shell died, and they fell to the bottom of the ocean, and gradually their shell dissolved, and then it precipitated as limestone. Well, at the same time, we had also some silicic, as in silica, organisms that formed siliceous sediment, and that would be the black here. That's called chert. Chert and limestone commonly occur together, and when I said siliceous, I meant silicious, silica, not salacious. So, what does this have to do with El Toro? These beds of limestone and chert are interlayered with the volcanic rock that forms El Toro. And it's only a few, 5% of the whole mass of the mountain is made out of this stuff. But it's really critical to the formation of what we call El Toro. Because this stuff doesn't erode as well as the lava rock, the greenstone. It's particularly resistant to erosion and weathering in arid climates. That's us, we're semi-arid. You go to the Grand Canyon, these big cliffs, the red wall limestone, 500 vertical feet of limestone, the Kaibab limestone, these are the formations that create the most resistant, are most resistant to the forces of erosion. You go into wetter areas like Kentucky. Kentucky's favorite is well known for a horse race and caves, limestone caves. In the wet climate, the limestone dissolves. In the dry climate, limestone resists erosion, and while all the greenstone erodes away, the limestone stays there. And if I told you I got this from the top of El Toro, you would understand then that this is why we have the mountain looking like a volcano. There's a big knob of limestone and chert right on top of the mountain, and everything else has been eroding away on all sides of it. So as much as we like to look at that iconic mountain as this prominent feature, strikingly up there, vertical in front of our faces, it's really just an erosional remnant. So here's another sample of limestone and chert. Are these making it all the way onto you guys?
Yeah,
Okay, what are you doing with it, Mark? What are you doing with it?
I'm giving that table over there.
Okay.
I have, no, it's at the back, yeah. Just go in
Oh, all right.
They'll come back here.
Okay, chapter 3.
All right.
I was told to speak about a few specific things, and then you guys can pepper me with questions. You've been hearing over the last couple of years about Anderson Dam. I take no responsibility for that. Same name, coincidental. When the dam was built, 1950, 51, it was built on top of a very minor fault. It was known. Construction accommodated that. It was also built just a half a mile, close to a mile, away from the active Calaveras fault. That was known. Actually, for that matter, Coyote Dam was built on top of, straddling the Calaveras fault, the active Calaveras fault. That was in 1935. The engineers knew that the Calaveras fault was active at that point in time, and they knew they were putting a dam on it. Sounds crazy, but at that time, they took immense measures to build the Coyote Dam much beefier than would otherwise be required. So they did take precautions there. Anderson Dam, there was not the need to take those precautions. So the dam is structurally built to accommodate the forces that they understood at that time. But you've been reading in the newspaper twice in the last year plus that the Anderson Dam could fail and send a cascade, a 35-foot high wall of water across the valley. Isn't that right, Marty?
I didn't write it.
Marty didn't write it.
I didn't write it.
No, absolutely not. Well, that scenario is possible. It is possible. Let me tell a little story or a little bit of the... When the dam was constructed, they had to carve out the sides of the hills to fit the abutment styles and the spillway and so on. And then they started building the dam up by bringing rock from the hills and placing it in the right ways. It's not just a pile of dirt. It's engineered. There's certain kinds of rock and certain kinds of soil in different zones of the dam. They call it our zone. Our dam has 4 zones, typical. And they build the dam on top of the foundation below. Well, what they did in those days was a technique of construction. in the base of the dam, the foundation of the dam, that we are discovering now is not the right way to do it. It's built on alluvium, sand, gravel, silt, and clay. And that alluvium that they put part of the dam on, at that point in time was deemed to be pretty hard, pretty dense, and would not respond to any adverse geologic process like earthquakes. That was the understanding in the 1950s. Well, okay, we have dams all over the state of California. They have the potential to be horrendously destructive to us and our properties. We have averted disaster in California a couple of times, and yet I can say that because they are so dangerous, dams, they are pretty safe. Because we have California Division of Dam Safety of dams, that requires the owner of any dam of certain size and reservoir capacity that they monitor the dam and that they do periodic investigations to make sure that the dam is performing according to the current standard of the science. And so every 10 years or whenever there's a discovery or a breakthrough on science, our Santa Clara Valley Water District is asked to do an evaluation, a reinvestigation. So 3 years ago, Anderson Dam was investigated, and they discovered that this alluvium underneath the dam is about 15 feet thick, thicker than they thought. And maybe it's not so dense as they thought it was. And we have learned in the last 20 to 30 years that alluvium of the gravel size has a potential to turn to liquid. The term is liquefaction during a big earthquake. So the preliminary study 2-3 years ago said, we discovered this alluvium and it might have the potential to liquefy under an earthquake. We don't really know. We got to do some more studies, some more holes. And so Water District said, we better do those studies. And meanwhile, Division of Safety of Dams says, take precautions because we don't want to take any risks. And so even though the probability of such dam failure might be there and be very, very low, the consequences of a dam failure are unacceptable. So the studies have continued, and I can tell you at this point in time, and I don't have, maybe Steve or Marilyn know more about it at this point in time through the political conduits, but through the technical conduits, I can tell you that well, they write these reports in English.
Greek to me.
If the reservoir were at capacity, meaning water's coming over the spillway, and if Coyote Reservoir upstream Coyote Creek were at capacity, meaning water's coming over the spillway, if we're setting the stage, then if an earthquake were to occur with the maximum possible on the Calaveras Fault, maximum possible is 7.5 Richter magnitude, and if that magnitude earthquake were to occur right opposite the dam, right 2 kilometers away, then we could have the potential for dam failure. Okay, how do earth-filled dams fail? Slowly. They don't collapse. But the scenario that we in the geological sciences are required to use is instantaneous failure, meaning you take the wand and you touch the dam and it evaporates. Well, so the scenario is that Coyote Dam fails, a wall of water rushes down, and the minute it hits the Anderson Reservoir, Anderson Dam fails. Now you do have a 35-foot high wall of water going all the way across the valley. Okay, probability of the 2 reservoirs being at capacity, pretty small. Probability that instantaneous failure, no, it won't be instantaneous. It takes hours, sometimes many hours, for an earth-filled dam to erode, because that's what happens. It doesn't collapse, it erodes. So chances of it being a tsunami-like wave are very, very low. And what would trigger all of this, those that are calling the shots say, would be an earthquake right there, right next to Anderson Dam. And I can tell you that the geologic record from studying the Calaveras Fault is we don't have record of any earthquake being that large ever. The typical earthquake the Calaveras generates is about a 6.2. We've had lots of those. And prehistoric earthquakes, we have ways of measuring the displacements in the soils and the sediment and alluvium. We can tell, we can calibrate. And there's nowhere in the geologic record that an earthquake of 7.5 magnitude has ever occurred. And our geologic record that we've been able to study goes back 4,000 years perhaps. Mechanically, the fault doesn't seem to want to rupture or break all at once, the whole 100-mile long fault. It tends to break in segments, depending on who you talk to, 2 segments or 3 segments. No matter how you divide up the segments, the largest earthquake that could be generated is a 6 or 6.2. So the probability that we will get a 7.5 magnitude when the reservoirs are at capacity, pretty low. So the probability of that worst case scenario is pretty low. However, that doesn't stop the governing agencies from saying, take precautions. And right now, the reservoir is 47 feet below spillway. Something like that.
It's at 60%.
So
Yeah.
what would that end up creating? If we had the earthquake, what would that?
If we had the earthquake and the worst case situation were to happen and that alluvium under the dam were to liquefy, then there would be the shell or the outer casing, if you will, of the dam would be at risk, and that could fail in landsliding, be a big slump. The face of the dam would slide down. But given the geometry of the dam and the mechanisms of landslide failures, it would only fail so that the crest of the dam would drop to something like 30 feet below the current crest, something like that. Don't quote me on those numbers. And so the reservoir level is being kept significantly below the level that the crest would fail down to. Is that okay? Is that clear?
Yeah.
So there would be no.
There would be no overtopping of the dam. Right. And all those doomsayers that predicted the rupture and so on 3 weeks ago, they would never see that 35-foot high wall of water. Aw, shucks. Okay, the last thing to say about that, the dam, is that it looks like there will be the need for some sort of hazard mitigation, or if you will, retrofitting of the dam to accommodate these low probability but excruciating events. And all I can see down the pike here is that there will probably be some major earthwork going on the dam for 3, 5, 10 years to fix the dam, and it may cost, well, to say tens or many tens of millions of dollars.
They did make a presentation to Holiday Lake Estates Maintenance Association last Thursday night, and they told them that they're going to be studying this over the next year, and they don't have a plan yet, and they won't have a plan. The big rumor going around was it was going to be drained for 5 years, but that is just a rumor. They have no plan yet. They're studying.
Great.
And it's going to be a while.
Yeah, let's not rush them. No, we want to make sure that it's right. It's just too much.
What types of things would mitigate? Would it be something having to do with the alluvium, or like making it more dense, or is that one of the things that they would do?
We call it ground modification. Yeah, you go down and you stiffen up the alluvium. Really hard to do with the dam sitting on top of it. Really hard to do. Well, one of the options, build a cofferdam and then rebuild the entire Anderson Dam by taking out the alluvium. That appears to be less practical than some of the other possible solutions. I don't know what they would be. I can imagine what they would be, but I don't want to say those things. But it will be a very big deal. Something that I was asked to address was why we have 2 rivers in Morgan Hill. I want to make sure we got all the rock samples out there. Why we have 2 rivers in Morgan Hill that run in opposite directions. And for this, I need to wave my arms a whole lot because you need 3 dimensions here. Remember that, well, you probably don't remember, but I was there. After the glacial epoch, the Santa Clara Valley, a linear valley, had its headwaters in Hollister. And an ancient creek flowed from the hills around Hollister straight to the bay. I say after the glacial epoch because during the time of the glaciers, we were experiencing 2 to 3 to 4 to 5 times as much rainfall as we have now. And all this loose alluvium that was out throughout the valley wasn't there. It was, I call it, Santa Clara Canyon. It was several hundred feet, maybe 500 feet deep in Morgan Hill, deeper elsewhere. And so we had a canyon with no alluvium in it, and the headwaters in Hollister, and the Santa Clara, I call it Santa Clara Creek. Why not? I can name it, I'm inventing it. From Hollister flowed all the way through the valley out to, well, it wasn't the bay then. The creek flowed all the way through this canyon, and then directly out the Golden Gate into the ocean, which was offshore. There was so much water in the earth tied up in glacial ice that the sea levels all over the world were hundreds of feet lower. So you take out hundreds of feet of ocean, you disappear a lot of the coastline, or you change it a lot. So, okay, our valley, like most normal valleys, has a headwater and a mouth to it out that way. The Salinas Valley, same thing. Linear valley, it also flows north by coincidence. The Nile Valley, coincidence, is another. They call it an upside down river because it flows up on your map, but the water's really flowing down. Anyways, it's a linear valley, and it flows from headwaters to the ocean. The Sacramento Valley, the San Joaquin Valley, flow from headwaters, and they join at the delta in Stockton and then out through the gate. Well, something happened in our valley that changed and gave us 2 rivers going in opposite directions. Since I can't use the slides for projection, I made a little quiz cards here, flashcards. I'll pass them around because I can't show them, but we start and then we go through and so Marty, when you read this, don't tell the answer. So we've got Santa Clara Creek flowing all the way to the ocean, and we have the largest creek by far that feeds into our valley is Coyote Creek. The drainage basin for Coyote Creek goes all the way through all of Henry Cove. It's 100 times bigger than any creek elsewhere that feeds into our valley. So we have this canyon, and this monster tributary, the Coyote Creek, is eroding from the hinterland up there at Henry Cove and bringing alluvium down to the valley here. It comes through the notch in the Diablo Range where Anderson Dam now situated. And it carries all high energy water tumulting down looking like the Merced River coming out of Yosemite, bringing all these rocks and boulders and sediment, and it issues right out into the canyon, and it deposits all these boulders and sand and gravel and stuff right there in the middle of the valley. Well, that sort of causes a little trouble for our axial creek that starts in Hollister. It's trying to reach the bay. And now all of a sudden there's this big alluvial fan of sediment from Coyote Creek right there, right opposite where Morgan Hill City is right now, Cochrane Road. And so as our Santa Clara Creek, the one I invented, flowing north, comes to this alluvial impediment, an alluvial fan, it has a hard time getting around, so it slows down and deposits its sediment. So we are filling the valley with alluvium at the same time as we are blocking the flow with the alluvial fan here. Eventually, that goes on long enough that the alluvial fan from Anderson, that comes through where Anderson Dam is, Coyote Creek alluvial fan blocks entirely the flow of the axial creek trying to reach the bay. Now we get a lake. The water can't get around, so we wind up with a lake. Call it Santa Clara Lake. Call it Martin Cheek Lake. I don't care, anything. And yet that's a very transient feature. It shortly realizes the water, it's got to go somewhere. Gravity makes it go. It's got to go downhill. So it turns around, and the lake fills up to a point equal to the, or almost equal to the alluvial fan, and forces the water to go the other way. So we have Coyote Creek coming out of the Diablo Range, comes into Santa Clara Valley, continues its journey north to the bay, and now Yagas Creek and other creeks in the Santa Cruz Mountains come into the valley right here in Morgan Hill, and it makes a right-hand turn and goes south out to Pajaro and the Pacific in that direction. So here we are, right in the middle. The highest point in our valley is Cochrane Road. It's strange. The middle of the valley has the highest point. That's not a common feature in the geologic world. And so as a consequence, water flows downhill. Water from Cochrane Road will flow downhill to the bay and downhill to the Pajaro.
Peter, how unusual is this?
Pretty unusual because I just made it up.
I actually heard of it before.
Very unusual.
Very unusual.
Yeah, 1 in 1,000 creeks may have this kind of a situation.
So Cochrane Road, sort of the continental divide for
Yeah.
Santa Clara?
Right. Yes, the continental divide.
Go ahead.
This is real risky.
You start.
Merv, no, go ahead.
No, it's okay. But I had a question. I was wondering, how are you able to predict the maximum magnitude of an earthquake like you just did?
How do you predict the maximum magnitude that a fault is capable of generating?
Right.
Empirical. This science of seismology really only began not even a century ago. And we haven't had a whole lot of big earthquakes that we've been able to study. But you just plot them up on a graph. How long is the fault? How big is the earthquake? And you get a whole lot of scatter on the graph, but you generally are able to make a correlation there. But then it gets complicated because some faults have bends in them and behave differently where there's a bend. So it's immensely complicated and I don't want to say immensely imprecise because we're getting pretty good
More
at it.
precise all the time.
Yeah.
You have more monitoring stations.
Oh, we monitor the heck out of our faults. Yes, we definitely do. Not as well as the Japanese, but that's another story. Somebody advised me that there's a special rock in Morgan Hill that I should say something about. That's what y'all came for, right? So I saved the best for last? What is that rock? Shoot, yeah. Yeah. Works. I do have a bunch of samples. They're tied to the boxes, so you can't take them out. What makes Poppy Jasper is something pretty unique. It's not entirely unique. I have to be careful with this terminology. Poppy Jasper is a type of orbicular jasper. Orbicular, orb, as in circle, as in orbit, sphere. The jasper we have is a type that forms in little concentric spheres, meaning picture a BB, and then a marble, and then a ping pong ball, tennis ball, etc. Bigger. Concentric around each other so that it looks like an onion skin almost, different. And our jasper is orbicular, which is slightly unusual in the jasper world. No, pretty unusual, but not unheard of by any means. So remember that puppy jasper is a specific type of orbicular jasper. Why do we call it puppy jasper? Because it has fairly unusual, but not unknown, poppy orange colors in some of these concentric rings. You'll notice as these samples go around, and those two samples, one is completely, if you will, naked. A sample just as I pulled it out of a creek. So it doesn't look very spectacular, but you can still see the orbs. Another one was cut and polished. You can see the orbs fairly nicely. I have two other samples here that have been tumbled, meaning you put them into a rock tumbler, put in grit, and it develops a very nice sheen to it. And so these will go around as well. Where was he? Of the different colors in poppy jasper are almost all a variety of red, orange, or yellow, or a slight brown. Those colors are all represent oxides of iron. Rust colors. Almost all soils in this part of the world have a brownish color, and that's because it doesn't take but a very little bit of iron in the soil to oxidize, and iron is a very strong color former. For instance, fires burn yellowish flames, yellow-orange, because sodium makes a very strong dominant color when it burns, and it masks out all the other colors. You can get a blue color of a flame or a green color of a flame, but we always see yellow because sodium is so dominant. In our soils and in our rocks, it's iron when it oxidizes. So what happens in the formation of jasper is it's fluid. It's a liquid, a hot liquid. It's like a volcanic liquid. And for some reason in the rocks around here, the country rock, the base, the bedrock, fractures open up. We got tectonics going around here. We have earthquakes. Ground's moving. Fractures open up, and from way down deep, in jets some of this hot siliceous fluid. Silica. Silica is just sort of like window glass. Sand. Very common. Well, you get silica fluids in the rocks, and then for some reason there's a little penetration of the host rock, and some oxide of iron gets in there. Now all of a sudden the fluid is not clear, like window glass or quartz. Now it has a rust color. Fe2O3, two atoms of iron and 3 of oxygen, has a more reddish color. Fe3O4, 3 atoms of iron and 4 of oxygen, has a more yellowish color. Limonite, is that right? We have a geology student here, by the way. She knows all this stuff. And she knows where I'm wrong.
I was trying to remember what Fe3O4 is.
Limonite or goethite or hematite or a bunch of these iron oxide minerals. And the chemistry of this fluid changes as it begins to cool. The oxides move around. And then they begin to precipitate, just like the fossil shells precipitated and formed limestone in layers. In the poppy jasper crevices in the bedrock formations, they begin to nucleate. There's another word for you. 3-syllable. That's a big one. Some impurity in the water, in the fluid, begins to attract molecules. And so they all come to the center. Like us orbiting the sun. We want to go to the sun. Well, someday we'll get there. Someday these iron oxide molecules come to the nucleus. And they begin to form that color. So you get like a BB of a deep red or yellow or orange, whatever it happens to be, the oxide. And then the chemistry of the water changes a little bit more, and now the next layer of iron oxide contaminated silica has a different color. And so these colors vary like the different rings of an onion. So in the sort of the genre of rockhounds, poppy jasper collectors, the more rings you have, the more different colors you have, the finer the sample. And the more precise the boundary between the different rings. on one of these samples, and I've got one up here, two of them up here, the boundaries are not very precise. If you go over to the Community and Culture Center in Morgan Hill, a very fine specimen of Papa's Jasper is on display there, and it's got, I think I counted 8 or 9 different rings at one point in time, and that's pretty unusual to find. And any other questions, Murph?
These are concentric rings, right?
Thank you, Murph. I hate techie guys that play games with me. That's all that I had prepared. So can I sit down now, Ken?
You can have a glass of wine.